Hey everybody. We've seen a single neuron act like a predictive model where we could feed it some inputs, like for example whether someone is pretty and intelligent, the weights that we attach to those different attributes, a bias or a threshold, those are synonyms now, and our model can predict for us whether we will find that person attractive or not. It's a pretty straightforward model, and in this video I'd like to kind of expand on it a little bit. For example, there's no reason why we need those numbers and not other numbers. And further, there's also no reason why we're limited to just two different characteristics for the person we might potentially date. So let's build on our existing model. So our model was, so we had our neuron body right here, which just symbolizes two things. It symbolizes a sum, like the weighted sum of attributes. And then there was this nonlinear step function, activation function thing. We had two inputs, x1 and x2, which was whether they were pretty and whether they were, I believe, funny. And we attach weights to those attributes. There was also a bias or a threshold. And if our weighted sum plus our bias was bigger than 0, or if the weighted sum was bigger than or equal to the bias, or negative bias, then we would spit out a particular value for y, which is either a 0 or a 1, right? Or hot or not hot. So that was the basic building blocks of our model. If I remember correctly, we had x1 had a value of 9 and a weight of 1. So very pretty. X2 was a 5, so only kind of funny. And that was really important to us. And we had a bias. And let's just make this bias negative 10. It's one different number than we had a couple videos ago. So if this describes our person, and these W's and B's, these weights and biases, describe our preferences, then will we find this person attractive or not? And again, there's a summation part and an activation part, the linear part and the nonlinear part. The linear part is a weighted sum. So we just take x1, weight it, x2, apply a weight. Let's add the bias, and then we'll see whether this thing, this z, is equal to 1. If z is positive, and if z is negative, z is equal to 0. Right, so we had our linear part and our nonlinear part. Okay, so let's apply these numbers. Now we've got here, just fill in the values right here. We have a weight of 1 times an x of 9, a weight of 8 applied to 5 for funny, minus 10 is equal to some z. And let's calculate that real quick. That's 9 plus 40 minus 10. So that's 9 plus 30, which is 39. Hey, that's a positive number. So applying the nonlinear part, that's this part, applying the nonlinear part, since z is 39, which is bigger than 0, this implies that y is 1. So we find this person attractive. It's plausible, but you might say, Professor, this is way too reductive. Changing colors here. I said, first of all, I'm not quite so superficial. I don't apply, a weight of, well, I guess that'd be very unsuperficial, a weight of 1 on prettiness. There's no reason why the weights actually have to be positive numbers. Maybe pretty is a bad thing. Maybe you feel like you want to avoid pretty people because, they've got issues or something, or they're high maintenance. I don't know. It could be any number. You might say, that 2 characteristics, I need to know more about the person. Not only do they need to be pretty and funny, but they need to be intelligent as well. So maybe we need a third attribute. Intelligence. Okay. Now, let's, this intelligence, this X3 will need a weight. And we got to know what our preferences are, how important intelligence is to us. And we can see if this person is attractive or not. Let me clear this thing out. Let's get a whole new set of numbers and just work out another example. All right, so we have now the body of our neuron, weighted sum, and the step activation function. You don't usually have to write this, so just as a reminder to us what the steps are. And we've got now 3 inputs. So we have x1, x2, x3. We give the weights. And we also have a bias term. Bias. And all right, that's it. Those are the parts of our model. Let's make up some attributes for our hypothetical person and some weights for our hypothetical preferences. So we could do this like as a table. We could say x1, x2, x3. X1 is, let's make up some numbers, 5, 6, and -3. Again, just making up numbers. So that's a 5 that we're feeding in for x1, 6, and a -3. And then we need our weights. And we could do, we could do 1, 10, and 3. All right, well, we need our bias. Let's stick with -10, just because, why not? And see if this describes our decision-making process. This is the person we're trying to decide about, and these are our preferences. Then what does this model say? Will we find this person hot or not? All right, so the process should start feeling a little natural now. We have our weighted sum. So we're going to add 3 x's, but we're going to weight them first. So we apply a weight to each of those inputs. Calculate as, don't forget about the bias. And then if z is positive, y is 1. If z is negative, y is 0. Now we just plug in values. All right, so what is this? Let's do this real quick. We have a weight of 1 applied to x1 of 5. A weight of 10 applied to a value of x2, x2, which is 6. We have a weight of 3 applied to an x value of -3. Then we have a bias of -10. So what does that come out to? So we get a 5 plus a 30 minus a 9 minus a 10. Ooh, all right, things are getting interesting. So we get a 35 minus 19. And so z is 16. And it's still bigger than 0. So since this thing is bigger than or equal to 0, we're guessing you're going to like this person. We don't need to be stuck with 3 attributes. We could tack on a 4th attribute. I'm running out of space, right? So maybe x4 is whether they drive a Mustang or not, or their wealth. whatever. There's actually no limit to the amount of attributes that you might find attractive or unattractive. And likewise, there's no limit to how many things you can add together to come up with a score for the person. And if the score exceeds a threshold of B, then we like the person. Alternatively, if that score with the bias is bigger than 0, we're going to like that person. Now I want to show you a little bit of a shortcut to actually writing out this whole thing like this sum in this tedious way. I mean, I like it because it's very explicit, but in some various textbooks, you might see just something like this: W times X, and maybe they'll throw in a B there. And W dot X with that multiplication sign, a little dot, is shorthand for something. It's usually you see it in algebra as a multiplication, but if you're doing vector algebra, linear algebra, then the W and the X is they're these little vectors, and that's called a dot product. Now, if you haven't seen this, it's not a big deal, but really all it means is you're going to take a vector. A vector is just a list of numbers. We're going to call this X. So this X is the following list of numbers. We're going to take this list of numbers, 1, 10, 3, and then the dot product between two lists of numbers, you're going to just take the corresponding elements and multiply them by each other, and then add them up. So it's 5 times 1 plus 6 times 10 plus negative 3 times 3, which is this part right here. Right? And then you just add on the B, which is, subtracting it, adding a negative 10. So I just want to make you aware of this function in linear algebra called a dot product. It's a function that's applied on a list of numbers, a list of two numbers. Those lists have to be the same magnitude, so a list of 3 things times another list of 3 things. And when you multiply these, or dot product these guys, you're just multiplying the corresponding entries and adding them up together. Now I bring that up because, you'll see it in a lot of textbooks or maybe even some research papers if you're reading those. But you'll also, you can apply it in Excel to make your calculations a little bit easier. So let me bring up Excel and show you how it does that. Okay, so here's Excel. And I'm just going to type in the values, the 3 values for x, x1, x2, and x3. There were 5, 6, and negative 3. Our weights were 1, 10, and 3. The bias was negative 10. And let's see, I'll show you 2 different ways to do this in Excel. And the first is to calculate z long ways like this, and then apply the step function. And the other is to do this thing using some linear algebra. All right, so let's do z real quick. All right, so I'll show you 2 different ways. We want x1 times w1 plus x2 times w2, that's cell B3, plus x3, which is in cell A4, times w3, which is the contents of cell B4. And then I want to add the bias, which is in cell C2, and we hit enter. Ooh, did I do something wrong earlier? I'm getting a different number. Didn't I get 16 before? I did do something wrong. Back here. 10 times 6. 10 times 6 is not 30. I don't know where that came from. That's 60. So I'm off by 30. Let's fix that. That's horrible. That's embarrassing. All right, so this is 46. Okay, so that's the long way of doing it. Saved me, caught one of my mistakes. And then y, we can apply an if function. So if this cell is bigger than or equal to 0, then hot, otherwise not. Bigger than or equal to 0, hot, otherwise not. So yeah, they're hot. So well, what about a different person? What if you know, we had different preferences, so we're very superficial. So this was important to us, and this one wasn't as much. And this person was, you know, was fairly unattractive. And let's give this person a lower score here, 2. And yeah, that's good. Let's make this. Let's make that a 4. So here we've got these 3 characteristics. So different person with different weights. We have our same threshold, our same, you know, standard of, you know, what we are looking for in a person is -10. And this time when we apply it, we get a linear score of -2. Since that's negative, this person is not hot. All right, so that's one way of doing this product, is by just spelling out this thing in gory detail. But what I'd like to show you now is a different built-in Excel function called sum product, because that's what a dot product is. We're taking multiple, producting something, we're multiplying something, and then summing them up. So here we go, sum product, and now we give it a range, an array. We tell it all of these values, put in a comma. We want to sum product those values with these values. In other words, we want to take 1 times 10 plus 2 times 5 times -3 times 4. Say that again. We want these products, and we want to sum those products. Then we're going to just tack on this, and we get our -2 again. So this is, you know, I think easier than spelling out A2 times B2, A3 plus A3 times B3 plus A4 times B4. And maybe it doesn't seem that way right now, but we only have 3 attributes. What if we had a bunch more? Then I definitely don't want to be spelling out all of the sums and products. Let's throw in an example. Let's add some cells here. Let's make this a little bit bigger. And let's add some attributes. So again, I'm just making up numbers. We have -2, 4, oops, well that works too. 6, -10, and we need some weights. Weights can also be negative. Okay. All right, now to do this lengthy-wise, we would have to go this times this plus this times, what is it, B3 plus A4 times B4 plus, I mean, oh my goodness, this is just horrible. I'm going to stop. But we could just use, we can use that trick I showed you, sum product. That's sum pig. Sum product. I want you to take the dot product of this vector of numbers dotted with this vector of numbers, and then throw in a bias. We get a -16 for this particular person with these preferences of ours. We would not find this person attractive, not hot. This sum product is nice, right? So it isn't just, it makes for easy formulas on paper, but it makes your calculations a whole lot easier. The strength with artificial intelligence models is it can consider tons of information. We're not limited to just 7 attributes for a person. We could have 10,000. Heck, we could have more than that. If you're looking at an image, for example, it's plausible that we could have a neural network look at a picture. And how does it do that? It has to look at every single picture of this person, every single pixel, and somehow synthesize it and come up with an idea of what this person looks like. So what you'll see later on in the course is that each individual pixel in a picture is an attribute. It's one of these. So if you've got a 100 by 100 pixelated image, that's 10,000 X's. I definitely can't be typing, X1, W1, X2, W2 down to like X10,000, W10,000. But it turns out all you need to do is just do sum product of A2 to A10,000, B2 to B10,000, and Excel does all the calculations for us. Or Python will do it, or C++ or something like that. So the dot product is your friend. One final thing I want to squeeze into this video is this right here, this tacking on of the bias. See, we don't actually need to do that. We can fold that into a dot product. Basically, what we can do, to go back to our pen and paper for a moment, and let's get orange this time, is you see how we just had added this bias? This part was plus B. Right? Well, what we could have done is just included B in our list and then tacked on an artificial X that's always equal to 1. And now when we dot the X's with the W's, we have just one more entry to deal with. So we still do 5 times 1, 10 times 6, 3 times negative 3. But now we'll do negative 10 times 1. Right? We just need to basically squeeze in here a 1 and the bias. Ignore that part. And now when we dot them, we get everything that we need. So we can literally just fold in the bias into this W matrix. We just need to increase the length of X by 1 unit, by 1 more value, and make sure that it's a 1. Okay, so that's how you apply the dot product in a neural network model, in a neuron. Right? We've also seen that you can increase the number of X's however much that you want. So if you have very well-defined preferences over who you find attractive, you get a list of 100 things or 10,000 attributes that this person must have. As long as you can apply some weights to it, then you can just take a weighted sum and see if that weighted sum exceeds some threshold value. We've left one question kind of unanswered though, and it's where do those weights and biases come from? In the videos we've done so far, we've just kind of made them up. We just said, well, what if, if you were going to come up with a list of how important they are to you, I like this kind of person, I don't like that kind of person, and you can kind of off the top of your head come up with weights. But it turns out that the strength of AI models is that the AI, the process of training an AI is the process of learning descriptive and powerful weights and biases for your model. What we're going to do is feed a ton of training examples into the model. And at first it's going to, not be a good model, but it slowly starts learning your dating preferences, whether you swiped left or you swiped right. And that gives the AI data to work with. And the more data it has, the more it tries different weights and biases. And eventually it gets a set of weights and biases that seems to mimic your dating preferences. And hey, all of a sudden this dating app is really powerful stuff. Now it can start recommending people to you that you haven't swiped left and right on, but it thinks they're likely to be a good match. So we'll see how AIs learn weights and biases in a video or two from now. All right, thanks for listening. Bye-bye.